Okay guys, in this video lesson we're going to introduce our next unit, which is all about gases. Okay, in our previous unit we talked about intermolecular forces, and we talked a lot about the different states of matter: solids to liquids, liquids to gases, and so forth. In this unit we focus in just on gases themselves because they have some very unique properties alone. Okay, so here we go. First thing, let's remind ourselves some things that we already saw from our previous unit about gases. Okay, so this is not a new slide for us. Recall that gases are able to expand to fill any space. They are compressible, and they're free to move with no attractive forces. Okay, these three parameters are going to be kind of the key piece of how we go through this unit. They are based on what we call the kinetic molecular theory, which we will cover here in a second. And then lastly here, we have four variables in which we deal with when it comes to gases. We have pressure, temperature with an E, sorry, I'm missing my E there, amount, and volume, okay? Notice in these four, the type of substance does not matter here. So in this unit, we're going to be talking about gases pretty generically. We really don't talk much about helium versus nitrogen versus oxygen versus carbon dioxide, because for our basic properties of gases, they all act the same. So being carbon dioxide versus nitrogen, really no difference in basic gas properties. All right. Now, here's what the kinetic molecular theory tells us, and we have different parts of it. All right. So first part of this theory is that molecules of gas are going to move rapidly. Okay, so they move fast in constant linear motion. All right. So we're looking at like a box like this. If you have a gas particle, it is going to move in a linear fashion at a high rate of speed. Now, it will change direction, but only when it contacts another molecule or the wall of a container. Okay, so you can almost think like a game of pool or billiards where they move and they constantly going to keep moving and bouncing off each other until they hit something and they'll bounce off and bend and go back and forth. Now, what that means is gas particles don't fly in curves. They don't turn in direction on their own. They aren't pulled towards things through IMF. None of that kind of stuff exists. We have to kind of assume there are no intermolecular forces for these gases. Okay? And we make that assumption because we make one other assumption. We're going to assume that real gases that we deal with in our everyday lives act as an ideal gas. Okay? Or under ideal scenarios. All right. Now, what is an ideal scenario? All right. First one, the collisions between the molecules are completely elastic. Now, what that means is elastic collisions in the world of physics are one where there's no energy lost. Okay. So when two gas particles collide and hit each other and bounce off, what we're going to assume there is that there is zero energy lost in that collision. Okay. Now, in the real world, especially with bigger things, there's always a little energy loss. But for gas particles, because they're so incredibly small, because the repulsive forces they have between the electrons, that kind of stuff, we can make this assumption, and it's a good assumption. Okay, so no energy lost in collisions. Number two, there are no attractive forces between molecules of a gas. Okay, we know IMF exists. We know there are intermolecular forces out there. However, because the gas particles are so small, because they're moving so fast, and because they're spaced so far apart, typically speaking, we don't see that those intermolecular forces that exist change anything. Okay? So yes, they do really exist. We're going to assume they don't because their force that they have is negligible. So the amount of attraction they create in under normal conditions has no effect on how a gas actually works. Okay, so we're going to assume that there is no intermolecular forces for ideal gases. Now here's the last one, and the last one is probably the most confusing of the three to actually kind of wrap your brain around. In this one, we're going to say the particle itself has no volume. Okay, and what we mean by that is if we take a look at gases and the individual atoms of a gas or the individual molecules of a gas, the actual space that the physical part of the atom takes up, we're going to assume is zero. Okay? Now that seems kind of weird, right? Because like, wow, how can we assume there's nothing there? But you got to remember, for gases, they expand and they fill their containers. So if you think about, let's say, the air in this room that we're talking through, there are obviously gas particles in here, but they're so spread apart that the distance between them is so great that the actual size doesn't matter. Okay, so think of it this way: if you're doing a road trip and you're heading from Minneapolis, let's say, down to Texas, down Interstate 35, and as you track your miles, when you do that, you really don't account for the little towns you have to drive through and saying that there's extra miles there because they're so small. Okay, it doesn't really matter. It's kind of like, okay, maybe you're going to drive to Blaine to go to a soccer tournament at the big soccer complex there. If someone says how far away it is, you say, oh, it's this many miles. You don't account for the extra 100 feet you have to walk from your car to get to the soccer field. That extra 100 feet is negligible. Okay, it exists, but in terms of how far you actually travel, it doesn't mean anything. Same idea here. Okay, so the space between the particles is so big that the actual size of the atom means nothing to us. Okay, now we're going to make sure that these ideals hold true for ideal gases. If we have time at the end of this unit, we might talk about what happens when the ideal scenarios collapse and we have to deal with some real things that go on. Okay, what that means to us is if we have real gases, which we'll be talking about real gases in here, they're going to act like their ideal under normal temperatures and pressures. Okay? Normal temperatures and pressures for us are things that are about our temperature in our world and hotter. And pressures for us are going to be things that are about our pressure and less pressure. Okay, so we're not talking about pressurizing containers, and we're not talking about really cold scenarios. So really we're looking at warmer things and less pressure is the best way to look at ideal gases. Okay. Now, what is pressure? So for us to talk about this, we have to have a good handle on pressure itself. Okay. So pressure is created when you have particles striking the surface of a container. Okay. It comes from the movement of particles colliding with the walls of the container. If you think about it, that's how we get pressure, right? Something bangs against the wall, a gas particle flies in and it hits this wall. That collision creates a force. That force causes pressure against that wall. You do that a billion times over, and now you create pressure on your substance. Okay. Now, how do we get more pressure? Well, more particles. So if you put more particles in here, there'll be more collisions. More collisions means more pressure. Or we can make them move faster. Okay. So the idea behind pressure is how do we get pressure? It comes from collisions. All right. So the more collisions we can create, the more pressure we can create. All right. We can do it by speed, or we can do it by sheer quantity of particles. All right. Now, when we generate pressure, there are three ways that we label it. I wish there was only one, but we got three. Okay, we label things in atmospheres of pressure. This is a system based off of what our typical atmospheric pressure is on our planet at sea level. Okay, so if we talk about an atmosphere of pressure, or 1 atmosphere of pressure, that would equal normal pressure in our world at sea level. We use millimeters of mercury. Millimeters of mercury has been around for a long time. It's because that's the first way we were able to accurately measure pressure. What we would do is we would actually put mercury in a tube system, and we would leave one end, or leave actually 2 different ends open to the environment. And as the atmospheric pressure pushed on a tub of mercury, it would push some of that mercury up a column, and it would travel up a certain distance or a certain number of millimeters. So we would measure that in millimeters of mercury. You may have seen this in the U.S. system of inches of mercury, talking about atmospheric pressure. Like, okay, the pressure is dropping from like 31 inches to 29 inches of mercury. That would mean like, hey, there's a low pressure system coming in. Same idea, but we just use millimeters because it's the SI system. And the last way that we measure it is in pascals. Okay, a pascal is actually a very, very tiny amount of pressure. This kind of comes out of the chemistry world, and so pascals being really, really tiny, a lot of times we actually work in kilopascals as we look at these. Okay, so as we go through the unit, you're going to see these different forms of pressure, and we should be able to convert between them. So here is your link between those 3 things. We're going to base it off of the atmospheric system, so a single atmosphere pressure. So in our world, 1 atmosphere of pressure is about 760 millimeters of mercury. Okay, you may have also heard this called 760 torrs. Okay, because torr is a word that people use for this also. So we have 1 atmosphere is 760 millimeters of mercury. An atmosphere is 101.325 kilopascals. I remember this one because of the radio station that we have in town here, 101.3. Okay, just remember the 0.25 part. Now, because these both are set equal to 1, that means there's 760 millimeters of mercury for every 101.325 kilopascals also, okay? So we should be able to convert between any pressure units we need to as we go through this unit, all right? So take home here, pressure is created through collisions, okay? How do we get more collisions? More particles, make them move faster. We have three units we use for pressure, and we should be able to convert between 3 of those. Now, atmospheric pressure itself, if we take a look at it, comes from the pressure exerted by the force of gases on our atmosphere onto things, okay? Here is actually a visual of that mercury column I was talking about before, okay? So to measure millimeters of mercury, they actually put a tub of mercury inside here. They took a vacuum tube or a chamber that was completely void of air, best they could, and they inserted it into this mercury. Well, because there's a vacuum here, the atmospheric pressure pushes down on this tub of mercury, and it pushes the mercury up this column, okay? Now, the height that the mercury rises up this column, that is directly related to how much pressure, how much push the atmospheric pressure is pushing down on this tub. Well, if this goes up about here, about 76 centimeters or 760 millimeters, that is our normal atmospheric pressure. So that's where that measurement comes from. It's actually a true column of mercury that was experimentally determined by the atmospheric pressure pushing down on stuff. Okay. Another way to look at atmospheric pressure, if you're dealing with a gas, that if you have an open chamber, if you have gas inside and you have gas outside, the atmosphere is always going to be pushing on that chamber, okay? The gases on the inside are going to push back because there's going to be collisions inside, there's going to be collisions outside, okay? And what happens is we again get this equilibrium established where the pressure that is from the atmosphere will actually equalize with the pressure that's inside with this gas if this is a movable piston head, okay? So the forces created for both will be equal to each other. This is important for us to realize is because we start dealing with movable pistons where things can slide back and forth, we can realize that any time that we deal with a movable piston, unless we're creating an additional force, the pressure on the inside that is generated because of the collisions will equal the atmospheric pressure on the outside of that, okay? As long as this is movable, okay? Now, if this was not movable, we lock it into place, we could definitely create an imbalance of pressure on either side if we wanted to, okay? Last part of this little video lesson is a review of kinetic energy because in this unit we're going to spend a lot of time talking about speed of particles and energy along with pressure, okay? So a quick review of that. Remember, kinetic energy is that energy of movement. Remember that the faster the object moves, it's higher the velocity, the more kinetic energy it has, okay? So we're going to talk about particle speed a lot in this unit, where you have things moving slower here versus things moving faster here. So the faster they move, the more kinetic energy they have, okay? That'd be over here. The slower they move, the less kinetic energy that they have, all right? And then that's going to relate us back to, again, another kind of review slide from our previous unit about temperature. So if we're talking about the speed of particle, the way we measure speed of particles, the way we identify the average kinetic energy of a system is through temperature, okay? So temperature will be one of our variables that we're working with here. That measures that average kinetic energy of a system, okay? Remember, you give particles more kinetic energy, they move faster. As a result, higher temperature, okay? If you remove kinetic energy from particles, they slow down. This results in cooler temperatures, okay? So the reason why we talk about these things is we're going to get into different gas laws here in a minute, and it's going to be a lot of conversation between volumes and pressures and temperatures, okay? And if we go back to our ideas about gases, pressure is a big piece of variables for gases. Temperature is a big piece. The amount, that's just moles, okay? So amount is in moles, and we've already studied what volume is. So pressure and temperature are kind of the two new guys in our world, okay? All right, guys, I'm going to end the video lesson here. Thank you.